All right, so the first one, right, Lewis structures. And so this is a problem that kind of ties into content that you're going to learn in organic chemistry. And it has to do with the fact, right, that being able to understand and draw resonance structures actually is really important for understanding, why certain reactions happen or why certain reactions happen at certain places. So in this case right here, right, what we're looking at is essentially a reaction where, NO2 plus attaches itself to the an aryl ring, right? So like a very similar to benzene, and there's specific sites, right, that it'll attack, depending on whether you have certain groups sticking off of them, will actually direct it, right? And that's actually incredibly important in organic synthesis, is being able to direct and pinpoint where something's going to react, so that way you can make the actual molecules you want to make, right? Especially when it comes to making like pharmaceuticals. So what I'm going to do, just because it's a lot easier for me to draw and write, I'm going to use what's referred to essentially as like the skeleton method of doing organic chemistry writing, right? And so in those cases, what we do is we just simply draw lines for everything that's like a carbon and a hydrogen, right? So this right here is what benzene is. And so that's the same, right, as if I had written, this right here, right? And so these are all, then, each one of those, points on the thing are all, the maximum number of hydrogens you can have. And it's a lot faster to draw, organic structures that way. And it's going to make it a lot easier for me to do it, to show what I'm doing right here. But again, right, I mean, if you want to just follow along, then on the key too, like I showed the different resonance structures. But if we're looking at this right here, right, in terms of figuring out what's going on, when you're drawing the resonance structures of anything, the first thing you always want to look at is, do you have any formal charges that are present? And do you have lone pairs that are present, right? Because both of those can always get moved around in those cases. And so, looking at this first example right here, right, where we have, the ortho binding, right, where it binds to the carbon that's adjacent to the carbon that has the OH group off of it, right, for the N2O, right, we can see that we have a positive charge. We can see that we have a positive charge right there. Now, that positive charge, right, it's not, right, that carbon isn't at a full octet, right, and that's why this isn't going to be a stable structure, so to say, right? And so that positive charge is going to want to essentially move its way around as best as it can, to actually get to a point where it can be stable, right? And so, right, and that's where the resonance structures come into play, right? So, I mean, boron and like all the group 3s, right, those all can have only 6 electrons on them. Carbon can as well, temporarily, right, but it'll very quickly undergo some type of reaction because it doesn't want to be at that point. But what we can see right here, right, is that we have a positive charge that's located on a carbon, and then we have a bunch of, we have 2 double bonds that are present within this ring, right, and then we have up here an oxygen that has 2 lone pairs, right? So there's a lot of different essentially characteristics that can get moved around in a resonance structure to form, new resonance structures, so to say, right? And so the easiest thing that you can always do is, if you have a formal charge that is on an atom that is next to another atom that has a double bond, right? So if we look at, right, so if we use this as an example, right, this one right here is an example, right? You can see right here that you have that positive charge, and it's right next to that double bonded group right there. So what can happen is that double bond, right, it can move essentially over in that case, right, and then I'll form a double bond between these 2 carbons right here, and then all that happens then, right, is that this carbon right here, right, that was previously part of the double bond, now that gets the positive charge. So that moves over in those instances. And so, if you draw out that resonance structure, and so I'm just going to draw it as like the skeleton form, right? So if you draw out that resonance structure, in that case, right? So you have NO2 right there, right? So now you have a double bond here. You still have that double bond that's up here, right? You still have your OH group up here, but now, right, the positive charge is jumped over, and now it's on that other carbon, right? And so that right there is a resonance structure, right, of the first one. And so all we did was we just simply moved the double bond over in that case, right? But we still have the same number of atoms. There's still the same number of total electrons. There's still the same overall charge in this case, right? So we have that right there. Now, again, what we can look at is in this case right here, you can see that that positive charge again is next to a double bond. It's next to two double bonds, right? But if we were to, mess with the double bond that we had just formed, right, that would just get us back to the original resonance structure, right? We're trying to find new ones. And so, right, because we still then now have another double bond that's right next to it, what we can then do in that case is we can move, again, that double bond over, right, and then move that positive charge over. And so, one of the reasons why, right, and so you get this, and you get this, and you have your OH right here, right? And now that positive charge is on that carbon, right? You still have your NO2 here. Now, just looking at this right here, right, we can already see that that positive charge that we have, right, that positive formal charge, it's actually spread out across 3 atoms at this point already, right? It's spread out across 3 carbons in that case. And so, one of the ways that when you have an electron deficient atom, right, one that isn't at a full octet, one way that you can stabilize it, right, is if you have a bunch of resonance available to actually spread out that positive charge across a bunch of atoms. Because now, right, if we were to just like be thinking, if this was right here, right, if we were just like thinking about it, we're like, okay, right, in actuality, there's only really a third of a positive charge on each one of those carbons, right, just from those 3 resonance structures right there, which is a lot more acceptable, I guess you could say, compared to just having the positive charge being like permanently located on that one carbon. And that's how, essentially a lot of resonance, structures can actually stabilize things that you would think aren't stable. And that's because, right, they're able to spread everything out. Now, so we have those 3 right there. And so now the last thing that we can think about, right, is that we have that positive charge on that, on that carbon that's bound to the OH group. Now, again, right, you have that positive charge. There's an OH group that is nearby that has lone pairs. And so those lone pairs now, right, those can get moved in to form a new resonance structure in that case, right, where it'll form now a double bond between the carbon and the oxygen. And now the positive charge, right, gets moved. And so if we do that, in this case, right, so we have NO2, and so we have OH, right, and so now we have a double bond between the oxygen and that carbon. Ugh, that's kind of ugly. Let me just redraw that. Right, so now you have a double bond between those two, but now the positive charge is on that oxygen, right? And the reason, right, that moved over, right, is that we had the electrons from the oxygen, right, that lone pair, move in to form the double bond in that case. And so now, right, if we're going through and counting all the electrons around the oxygen, right, what we have is 1, 2, 3, 4, 5, right? There's 5 around them, right? It's 3 that are in bonds, and then 2 are in a lone pair, right? That's 1 less than what it, normally has, right? Which is 6. And so that's why it has a positive formal charge in that case, right? And the same thing happens for all the carbons if we were to add them up in those cases too. Now, the thing is, right, if we look at the octet rule in this case, right, and we count how many electrons we have around the oxygen, we have 1, 2, 3, 4, 5, 6, 7, 8, right? There's 6 that are in bonds, and then we have 2 in the lone pair, right? So that oxygen has a full octet, so that's happy, right? If we look at this carbon right here, right, this carbon has essentially, right, it's, it's a carbon, and it has 4 bonds around it, right? And so those 4 bonds give it 8 electrons, right? So that's also stable. And the same thing is true for all the other carbons in the ring as well, right? So all of those meet the octet rule. And so, right, in this case right here, right, this right here is going to be the most stable resonance structure, right? And the reason for it being the most stable is because it meets the octet rule, right? You have the you know you know everything has the right number of bonds that it needs in those cases. Now, one thing, right, that might freak people out is because there's a positive charge on the oxygen, right, and the oxygen is electronegative, versus, right, if you have the positive charges on the carbon, and the carbons are less electronegative, right, so that would make more sense to be positively charged. But the problem is, right, in each one of those carbon cases, you don't have full octets for all of the atoms, right? So if we just use this first example right here, right, all of them have full octets, except for, this carbon right here, right? That carbon only has 3 bonds, and so that means it only has 6 electrons around it, right? So it's 2 electrons short of having a full octet in that case, right? And so that's why those aren't going to be the most stable resonance structure, right? The most stable resonance structure is going to be that positive charged oxygen species in this case. Right, and so that's the case right there. And so again, right, the way to approach doing any of these resonance structures is to, when you're drawing them out, looking at if you have formal charges that are, essentially on an atom next to a double bond, and that can be either positive or negative, right? They don't have to, only be positive, right? You can also do a lot of the same stuff with negative ones. All you're doing in that case, right, is just simply moving the negative charge around versus the positive charge like I was doing here. Or, right, looking to see if you have lone pairs that are nearby, right? Because then again, those lone pairs can easily move around in each one of those cases. Now, one thing too with the lone pairs, and that's in a different problem, I think that's in the week 5 packet, is that the you can have a resonance structure. It's not going to be the most stable resonance structure, right, in that case, right? But it's still going to be a valid resonance structure where you have essentially maybe a double bond and then a single species that has a lone pair next to it, right, adjacent to each other. But you can still move that lone pair into forming a new double bond, right, and then break that other double bond and then turn that into a lone pair on that, on the other atom. And you may end up with 2 formal charges in those cases, right? But that's still going to be a valid system. So, excuse me. But yeah, so that means so that's essentially how you have to think about drawing these resonance structures, especially if you have formal charges and lone pairs. Is always looking to see, is there a lone pair on an atom next to a double bond or even a triple bond, right? Anything like that, because then those should be able to get moved around in those cases, right? And the same thing happens down here, right? So if we do, the meta version, right? So now that NO2 group is 2 carbons away from the OH group in this case right here, right? We have a positive charge on this carbon right here. All right, awesome. The pen works now. Right, we have a positive charge on this carbon right here. I don't know why it says when. Right, and then we have a double bond right here. And so what we can then do very easily is we can just simply move that double bond over, and then what happens is that the positive charge moves over. And so if we do that, and then, draw that out, right, so we have double bonds there. This is still then the NO2 in this case, and then we have OH minus, right up, or OH, sorry, up there, right? And now the positive charge is over here. Now, one thing that you may be thinking is, wait a second, can't I take that, that lone pair, and could I move that over to, down here? No, you can't, right? That's too far of a distance for that lone pair essentially to travel, right? That lone pair is always only going to move from on an atom into a double bond, right? It's always only going to move, essentially those distances. And same thing with double bonds, right? Double bonds are only going to move from either from one, from its starting bond to forming a new double bond somewhere else, or it's going to move from being a double bond to moving to being a lone pair on an atom, right? And so those are the only 2 ways, right? You can't have a double bond move a whole bunch of distance, right? Because that's not how resonance works, right? You're talking about 2 different compounds there in those cases. So, right, so we have this right here, and then again we can do the same thing again, where now we have this double bond moving to over here, and so you have the positive charge down here, right? NO2 is here. This is OH. And so you have this double bond here, right? And so those are the only three resonance structures that you can have in this case. Right there, you can't move anything to here, right? Because these have hydrogens off of them, right? And the same thing up here too, right? So those are completely saturated in terms of the amount of bonds that that carbon can have in those instances. But now, right, if we go to the para example, so if we do para, again, right, we have our positive charge right here. Here we have our NO2 group, right? We have a double bond that's right there. And so what we can do, right, is again, we can just simply move that double bond, right, to in between there, right, and move that positive charge around. So we have this, right? And I'll just include the hydrogen on that group just so there's little to no confusion. Right, so we do that, and so now, right, this carbon right here has everything it needs, and so now the positive charge is on that carbon. Now, oh, and then there's still the double bond right here, right, that started off with. So now the thing that can happen is a positive charge can move into two places, right? So one way that it can move is you can have the double bond move to right here, right? And so then that case, what you then form is this resonance structure where the positive charge now is on the other side of the NO2 group. Or, right, you can do a resonance structure now where the lone pair again from that oxygen moves in and forms a double bond. With that carbon, right, that previously had the positive charge and moves the positive charge onto the oxygen, right? And so again, though, right, if we're going through and we're doing the octet rule around this oxygen, right, we have 3 bonds, so that's 6 electrons. 1 lone pair, that's 2 more, right? So we have 8, right? We have a full octet there. For this carbon right here, right, it has 4 bonds around it, so that's 8 electrons, so that's stable, right? Everything else has the number of, electrons that it needs, right, for a full octet. So again, right, this is going to be the most stable resonance structure. And so, going back to the question, right, where, not only was it asking to draw all of them, but also to, say which one is the most stable, right, to justify why, HO, right, the hydroxyl group acts as, a para-meta director. It has to do with the fact, right, that you can form completely stable resonance structures, right, where you have, full octets on all of the atoms in those cases, right? And so that means that that's going to be a much more, quote unquote, long-lived intermediate. So then now, right, any further reactivity that might happen can go back there. Whereas in the case of the meta, right, you're not able to form a truly stable resonance structure where everything has a full octet, right? Because all of those carbons in those cases, right, that have the positive charge, right, they're all short 2 electrons in those instances. And so, what can happen is that the NO2 can then pop off again. And so you'll never see any kind of that reactivity, right? And so it's much, shorter lived compared to the other two. And so that's why, those groups are referred to as being, parameta, or sorry, orthopara directors, is because they form stable resonance structures in those instances. Now, if we were to go and look at part B, which I accidentally labeled as part A, right? If we now have something that is, referred to as a meta director, we can still use resonance structures to show why they don't form the most stable intermediates, right? And why the meta directors form meta compounds more often versus the ortho and para, right? And again, this has to go back to resonance. So if we look at this species right here, right, we have this NO2 group right here, and you can, draw a whole resonance thing with NO2 where you move around the electrons on between the oxygens in those cases, right? But that's not interesting, right? That has nothing to do with what's, going on in terms of why it's a meta director, right? What we have to look at is where the positive charge on that ring is in this case, right? And moving that around. So if we look at this right here, right, we have a positive charge on this carbon, right? And the, where the NO2 is on the ortho position. And again, right, we have, the 2 double bonds there, and then we have the NO2 group. So what we can do is go through, right, and we can move the same way that we've been doing it before, move that positive charge around, right, and get the different resonance structures. And so the way that we do that, right, is, we have a positive charge here, right, and we have a lone or double bond right there, right, so that double bond can move over, which will then move the positive charge. So if I just draw this out, right, just gonna put that there, and then NO2H. Okay, and so now the double bond moved, and so we also have the double bond here, and so now we have a positive charge on that carbon. And so then now we can draw another resonance structure where, again, right, this double bond right here moves over, moves that positive charge. And so we have that right there. And so now, right, NO2H, and then, oh, I forgot the positive on that, right? We have the positive right here. We have this oxygen, and we have this oxygen right there. And so now we have a positive charge on that carbon. Now, one thing to notice, right, because of the fact that that nitrogen that's part of the NO2 group has a formal positive charge, and then the carbon that's bound to it right next to it also has a positive charge, right? You have essentially two formal positive charges right next to each other. This is actually very, very unstable, right? This is not a stable interaction at all. In those cases. And so, or not very stable, very unstable. In these instances, right? And so that because of that, you actually, promote even more so that reaction not happening at that site, because you're forming a resonance structure that is not stable at all, right? It wants to push away. It doesn't want to exist in those instances. Whereas in the case of the meta, right, if we go through and we do the same thing, right, we have our positive charge right here, right? Here's our NO2 group. When we're moving around that positive charge, right? And so if I were to just go and I were to move this positive, move that double bond over, in that case, what you get is right, that resonance structure. And so that positive charge now is not directly adjacent to the NO2 group, right? It's on a different carbon in that case. And then you can move it around again. And so when I draw the arrows, right, so you'll learn about that when you take Orgo. But what I'm doing is essentially just simply moving where the electrons are to a new location. You don't have to do that in this class, but it's easy when you're doing any of these things to just kind of keep track of what's going on. Right, but you have that positive charge right here now, right? So those are the three resonance structures that exist for the meta position. They're not optimal, right? Because again, they are all, essentially leaving you with three carbons that do not meet the octet rule, but you don't have one of them being incredibly unstable like you do in the case of the ortho, and also in the case of the para, right? Because if we go through and we do the para example, right, so we have our positive charge right here, and so if we move this around, right, so if I take this double bond, right, and I move it into here, right, so now it's here, so now the positive charge is here, this is this, right, so NO2, H, right, and then N plus O minus, right, and so now again, right, you have two formal positive charges right adjacent to each other in those instances. And so this is, again, right, very unstable. Now, right, you can also still do a different resonance structure, right, where you move that carbon around, or that positive charge around again by moving that double bond. And so you have plus here, and then you have these NO2, H, and O minus, right? And those are the three resonance structures you have for the pair, right? So all I'm doing in those cases, again, is, just breaking it down, is that I'm taking something that has extra electrons, whether it's a double bond or lone pairs, right? And I'm moving those around either into, forming new double bonds somewhere or to forming lone pairs. And so in the case of positive charges, right, if you have, either a lone pair or a double bond that is right next to it, right, you can always move those electrons over, and then all you're going to do then is, right, either move that lone pair to someplace else, or move the positive charge to someplace else, right? And same thing with negative charges as well. But that's, essentially B12, right? How you approach that. And that's why, when you get to orgo and you get to this right here, right, you can just think back to what you learned in 330 in terms of resonance and thinking about what makes a stable resonance structure and how that actually translates over to reactivity. To the person that's watching this, do you have like any questions, or is there anything you want me to clarify? Otherwise, I'll just keep going in these cases. I know I spent like half an hour on this problem, but a big thing that freaks people out about resonance, right, is not really being completely prepared for situations where the resonance that you have to do on the exam doesn't directly match what you may be familiar with from the textbook or very simple examples. But again, right, like when you're drawing resonance structures, the biggest thing is always to look for to see whether you have another resonance structure is to see, do you have a double bond available somewhere that's right next to another atom that has either a formal positive charge, a formal negative charge, or a lone pair? Because more than likely, then you can adjust that double bond and then move that lone pair or that charge to someplace else in those cases, right? And it's always, useful to just simply look at it and figure it out, just to see, right, like, does it exist or does it make sense, right? The biggest things that people mess up with resonance structures too is that they will draw, they'll move atoms, right? And so that's the biggest thing with a resonance structure, right? Is that atoms don't move; it's only electrons that move. So just an important point.